Welcome back, students. This is Equilibrium, and we're going to talk about strong acid-base calculations today. There's our objectives. You can read those on your own. Okay, so this lesson is about the 6 strong acids. We're not talking about weak ones today. The stuff that we do with weak ones will be different calculations. So just the strong acids. And of course, the strong base, hydroxide, at the bottom of the table. Okay, so this says strong acids completely ionize with water to form hydronium ions. Completely ionized means there's no reactants left over. 100% of the reactants turn into products. So for all the 6 strong acids on the table, that's what you see. There's not an equilibrium arrow. It's a 100% reaction. So if they said the pH of the hydrochloric acid was 0.10, we'd have to figure out what's the concentration of hydronium. So we would simply figure that out and plug that in for negative log, and then we're done. So if I have 0.10 HCl, I times it by required over given, which in this case is 1 over 1. 1 H3O positive or 1 over 1 HCl. HCl's cancel there. I've now converted to 0.10 moles per liter H3O. I plug that in, which means I just plug it in over in negative log. Done. pH of 1. So when it's a strong acid, that's the calculation. It's nice and easy. Weak acids, different. We got to use ice, but we'll do that in the next lesson. Hydroxide, same thing. So if we were finding POH, for example, we do negative log of hydroxide, but if the NaOH is 0.10, I times it by required over given to find my OH negative, to be able to plug that in into the negative log formula. And the same thing, POH comes out to 1. Now, if we did this, here's the little test here. This is what's a little bit different. Notice I have 2 hydroxides, so I'd have to times it by 2 over 1 if this actually worked out. So 0.20 moles per liter, and then I plug that in, and my pH is 0.70. It just so happens that barium hydroxide does not dissociate, so we wouldn't have to do all that work because we can't get a POH of something that hasn't dissolved. But if there were a 2-to-1 ratio, that's what we'd have to do. That's the whole point of showing you that. Okay. So here's some examples. I've got nitric acid. Let's find the pH. So I take nitric acid, I dissociate it, and it goes 100%, so not a backwards arrow. There's my number. I got to find out what that is by timesing it by required over given. So now I've converted to my hydrogen ion. And you'll notice I'm using the Arrhenius theory. I could have added water to this and transferred the proton. These are so easy, it works out the same way. So anyway, I plug in negative log of 0.05 and I get a pH of 1.30. Okay, same thing here. I got magnesium hydroxide. Oh, trick, this does not dissociate, so I don't have to do any work. And hydrochloric acid. So I could take HCl, dissociate it into its ions. Now, this one's a little trickier because they didn't tell us what its concentration was. We have to actually do the math. So I take my grams divided by my molar mass, divided by my liters, and that gives me my moles per liter after I cancel out grams, and I end up with moles per liter. So that number goes there. Required over given, 1 over 1. Same number, negative log that number, pH is 2.05. Here's one where back last year in Chem 20 you might have done a dilution, same thing. So they've told us that we have 500 mils of 3 moles per liter, and now we pour a bunch of water in. Now we're at 3.5 liters. What's that concentration? So I do my formula. C2 equals C1 V1 over V2, and I get my answer, which goes there. Then I required over given. It's the same number, negative log that, and that's the POH of 0.37. Okay. A pH plus pOH equals 14, so I could find the pH of it, which is 13.63, because the question asked for pH, not pOH. Okay, that's it. That's strong acids. Very quick. All done.